Good day. Let's continue looking at enzyme kinetics. Now we've looked at the regular activity of enzymes and some of the factors that are needed. In this episode, we look at inhibition of enzyme action. It is true that enzymes require specific conditions for activity. That means that an enzyme isn't necessarily always on. Sometimes we have to turn it off. Sometimes we have to boost the activity. Sometimes we have to decrease the activity. And that's because metabolic processes will vary over time. For example, when we talk about digestion, there's the hunger phase before you eat, there's the in-transit phase while you're digesting the food, and then there's the after phase when you're busy absorbing and processing the molecules that result from your intake. So enzyme activity can naturally be reduced through a process we call inhibition. So inhibition of itself isn't necessarily a bad thing. It can occur from internal or external factors. Now, in terms of inhibition, depending on how it's initiated, it may be negative, positive, or very mild. And in the most negative way, it can even be fatal. This inhibition can be reversible, which means that we change the conditions to something that's more favorable and the enzyme acts, or it can be irreversible. That means that once we've caused the enzyme to be inhibited, we are no longer able to activate the same enzyme units. So it is an irreversible process for that particular case. Where we have reversible inhibitors, they can bind at the active site on the enzyme or at some other site. One of the examples of enzymes that is irreversible in its activity, or one of the examples, of inhibitors for enzymes that is irreversible, is penicillin. And note that it's described as an irreversible suicide inhibitor. Think about what that means. That means that when you use penicillin, whatever enzyme is affected, it is going to be inhibited from acting, and essentially the enzyme will be turned off. So it's irreversible. Now you recall we looked at plotting enzyme activity with Michaelis-Menten, Lineweaver-Burke, and Haynes-Wolf. If we plot enzyme activity with no inhibitor, you'll see that we get this blue line. If we plot it with an inhibitor at a fixed concentration, we get the green line. And if we double the concentration of the inhibitor, we then get this pink line. And so notice that what is happening is that Vmax, or 1 over Vmax, remains the same. However, notice that the Michaelis-Menten constant is going to be affected. And so this plot, when you see changes like this, it indicates that an inhibitor is acting. What type of inhibitor? A competitive inhibitor. And what do we mean by that? We mean an inhibitor that is competing with the substrate for the same space. It's kind of like in enzyme musical chairs. So both the inhibitor and the substrate will fit into the active site. So either the enzyme is going to meet the inhibitor, in which case activity is blocked, or the enzyme meets the substrate, in which case the reaction proceeds. So in this case, no reaction. In this case, reaction. But whether it's the substrate or the inhibitor, they are both competing for the same site. If we're speaking about reversible inhibitors, they can bind either at the active site or at another site on the enzyme unit. So if we have no competition, notice that we get Km and Vmax. That will be our baseline. If we have competitive inhibition, then Notice that the apparent Km has changed, but Vmax is unaffected. If we have non-competitive inhibition, this time Vmax is affected, but Km is not. For mixed, we got a whole mess going on there so that they're both affected. And in uncompetitive, which is different from no competitive or non-competitive, we get a mixture of changes occurring. So by looking at a graph, you can actually say what type of inhibition is going on just by looking at where the curve hits the axes. What is the impact on Km? What is the impact on Vmax? If it's pure non-competitive inhibition, where S and I, i.e. the substrate and the inhibitor, bind to different sites on the enzyme. So if we look here, we see that in this case, we have the inhibitor binding at a site that is not the active site, while the substrate binds at the active site. So the substrate and the inhibitor bind at different sites. What does that mean? It means that the substrate can get onto the enzyme because that space is not occupied. It also means that the inhibitor can get on. So at some point you can have just the substrate or just the inhibitor or both. Or in the case of free enzyme, none. And so if we look at the Lineweaver-Burke plot of pure non-competitive inhibition, note that Km remains the same, but Vmax is decreased. And anytime we talk about inhibiting the action of an enzyme, you can expect to see some impact either on Km or Vmax, or both. And you can pause and study these slides, which illustrate what's happening in mixed non-competitive, where binding of the inhibitor by the enzyme influences the binding of the substrate. In other words, if I as an inhibitor take up space on the enzyme, I'm going to say to the substrate, well, hey, I'm already here. Where you looking? Why are you trying to come? Now, if it's uncompetitive, that's a special case. In that case, what happens is the inhibitor will only combine if nobody else is on the enzyme. If the substrate is already there, the inhibitor is like, man, you already reached, I ain't even trying to go there. So once the substrate actually makes it, the inhibitor is like, not going to be interested in going there. So the inhibitor only combines with the enzyme, the free enzyme, but not with the enzyme substrate complex. As mentioned before, inhibition can be reversible or irreversible. Penicillin is an irreversible inhibitor of the enzyme glycoprotein peptidase, which catalyzes an essential step in bacterial cell wall synthesis. What does that mean? It means if you take penicillin for a bacterial infection, the penicillin acts on this specific enzyme in the bacteria, thereby preventing or severely disabling cell wall synthesis. And without the cell wall, you're not going to get the bacteria multiplying, which means that you're going to have the bacteria dying off. This is why it's particularly important for you to take your full dose of medication, because the medication is acting on a time basis. And if you only take it for a part of the time, then those microorganisms that are stronger, they will return, or they will be able to reproduce, and their offspring may be resistant to what killed off the first set. And that's where you get antibiotic resistance. And so that is some information on inhibition of enzyme reactions. We will be looking at this some more in quite a bit more detail when we talk about the detailed mechanisms of this. Thank you for your attention.